The question that I have is, how do you determine the cohesion and friction angle of soil from triaxial test data? Now I'm going to consider two of the most commonly used laboratory test types in soil mechanics. First, the triaxial test, and then the direct shear test. I will talk about the test details a little later. For now, let's focus on the type of loading that we apply in these tests and how that relates to the Mohr-Coulomb failure criterion. In a triaxial test, a soil specimen is subjected to principal stresses sigma 1 and sigma 3 like shown in this picture. We call this sigma 3 because there's actually a sigma 2 as well, but the sigma 2 and sigma 3 are equal to each other, and therefore we just have to consider only one of the two-dimensional planes, and we could typically consider the sigma 1, sigma 3 planes. Typically, this stress is kept constant and sigma 1 is increased. Say the failure lines for this soil are these. I know I didn't show you this line before, but the failure could happen due to either a positive shear stress or a negative shear stress. Say at some stage the specimen is subjected to sigma 1 equals 30 psi and sigma 3 equals 10 psi. When I ask you the question, is the soil going to fail? We have the fundamental knowledge to answer this question now. First, we know a little bit about stresses now, right? We know stress is not a scalar, it is a tensor, and it will have several components at a certain point, right? We know a little bit about the Mohr-circle principle, right? The Mohr-circle principle tells me that even though these are principal stresses, if I take an inclined plane, there is shear stress on that plane, right? So if the combination of the shear stress and the normal stress on that plane satisfy my failure criterion, the soil could fail. So how can I verify when I have these two principal stresses whether the soil is going to fail or not? So this is what we do. We go ahead and plot the Mohr-circle first. We know these are principal stresses, right? And therefore one of the points should be this, the other point should be that. Obviously the plane with the lowest principal stress is going to plot right here, and the plane with the largest principal stress is going to plot over here, right? Supposing, say, the Mohr-circle turned out to be this. Well, what do you think? Is the soil going to fail or not? The Mohr-circle principle also tells us that every point on this Mohr-circle represents a plane, right? So if I take this point right here, that represents a plane. The shear stress on that plane is this. The normal stress on that plane is that. But for that normal stress, the failure criterion tells me that the shear stress should exceed this value. That's the failure shear stress, right? Before the material fails. But the existing shear stress is way below the failure stress, and therefore it's definitely not going to fail on that plane. Well, what about other plane? Well, we can go around and every point on the Mohr-circle lies below the failure envelope, and therefore the material is not going to fail. Well, I keep increasing sigma 1. When I do, at some point, obviously the Mohr-circle is going to touch the failure line, right? Okay? And at that point, I have two planes. The plane represented by this point and the plane represented by this point, where the combination of the shear stress and the normal stress plots right on the failure criterion. And therefore, the failure is going to initiate on that plane. We will denote the stresses at failure as sigma 1f and sigma 3f. So I'm going to take this top part right here and redraw here with some details so that we can do some analysis here. Basically, I want to find a relationship relating sigma 3f, sigma 1f, c and phi. We see that the distance to the center of the Mohr-circle is basically the average of these two principal stresses, and therefore x naught equals sigma 1f plus sigma 3f over 2, And if I subtract this from this, I get the diameter of the circle, right? And I divide that by 2, I get the radius of the circle. Now I draw a line parallel to this line right here, and from that we know this distance right here, right, is x naught sine phi, because this angle right here is phi. And now we also draw another line here to be parallel to this radius, and so this little angle right there is phi, and therefore this distance works out to be c cosine phi. In other words, this distance is c cosine phi. Now if I add these two, that should be equal to the radius, right? So here is my analysis. I know it's a bit lengthy, but I wanted to show you all the intermediate steps like this and this so that you can kind of follow through. So I'll let you follow through. Eventually, we end up with this equation right here, where Ka is defined as the ratio between 1 minus sine phi and 1 plus sine phi. When cohesion is 0, like in sands or normally consolidated clays, then the sigma 1f and sigma 3f are related by this equation right here. So if I have a sandy material, all I need is just one test. I will take it all the way to failure and determine the value of sigma 3f and sigma 1f. Then from this equation I can evaluate my friction angle phi. On the other hand, if I do have a cohesive material, then you can see there are two parameters involved, friction angle and cohesion, and therefore I'm going to need at least two tests in order to evaluate these parameters. But typically you would do maybe 3 so that you can kind of average it out. If I were to evaluate the shear strength parameters graphically, this is what I would do. If it's a sandy material, I would take the failure stresses sigma 1f and sigma 3f and plot a Mohr-circle first, and then draw a straight line such that it passes through 0 and tangent to the circle, right? So the slope of that line is your phi, the friction angle. But on the other hand, if I have a cohesive material, like I said, we will need at least two tests. So we'll take the results of these two tests, plot two Mohr-circles, and then draw a line such that the line is tangent to both of these circles. The slope of that line is your friction angle, and the intercept is the cohesion. By the way, it's pretty common to do this graphically. As a side note, I want to point out that this parameter Ka will come back again later on when we talk about the analysis of sheet pile walls, and this will come in the Rankine theory of evaluating the earth pressures. And this is called the active earth pressure coefficient. The next question is, can we tell the orientation of the failure plane? Well, failure planes, I should say. There are two of them. There's one over here, and there's one over here. F1 and F2. Of course, we are experts in Mohr-circle analysis, right? So I have marked all the relevant angles in this picture here. So we know that if I take this point, or the radius pointing to that point, and then rotate that counterclockwise through an angle of 90 plus phi, I'm going to get to F1, right? Well, what do I need to do in the real picture? Well, I take the horizontal plane and rotate that in the same sense, which is counterclockwise, through an angle half of this. So that'll be 45 plus phi over 2, right? And I get to plane F1. So this is one of the failure plane. This plane is represented by this point right here. And similarly, if I take this point, or the radius pointing to that point, and rotate it in the opposite direction, which is clockwise direction, through an angle equals 90 plus phi, I'm going to get to plane F2. And here I come and then rotate this horizontal plane and rotate it through clockwise through an angle equals 45 plus phi over 2, and I get plane F2. So what I have done over here, I have taken these two planes and marked them right on the specimen. So this analysis suggests that we should see some kind of conical failure like this, right? So in fact, most of the time you do see something like this. It doesn't always happen though. So usually for a over-consolidated clay or a dense sand, this is the mode of failure. But for a normally consolidated clay or a loose sand, usually the specimen fails by bulging, like either this or this. If there is no friction between the loading platens and the soil specimen, then you're going to get a uniform bulging like this. On the other hand, if there is friction, then you will see something like this. But something like this produces non-uniform stresses inside the specimen and leads to erroneous results, and therefore we should avoid this at any cost. Finally, I want to point out that this analysis right here is valid with or without cohesion. In other words, whether you have cohesion or not, the orientation of the failure plane is 45 plus phi/2 to horizontal. Let's do an example here. Here are the results of two triaxial tests. Test 1 gave us these failure stresses and test 2 gave us these failure stresses. We want to find the cohesion, friction angle and the direction of failure planes from the results of these two tests. We derived this equation in the earlier slide. We might as well make use of this. By substituting these numbers in this equation, we get two equations. By subtracting one from the other, I am able to first calculate a value for case of A, which came out to be 0.3889. But we know case of A equals 1 minus sine phi over 1 plus sine phi. So utilizing that equation, I get a value of 26.1 degrees for the friction angle phi. Then I can use one of these equations to get a value for the cohesion C. I use equation number 1 and I got 14.03 kilopascal for the cohesion C. We know failure planes make an angle of 45 plus phi/2 with horizontal, which works out to be 58.05 degrees. We'll talk about the analysis of direct shear test in another video.